Okay, folks, I'm going to try to walk you through a few of the pages from the middle of Chapter 3. So we're going to talk about gas expansions in more detail, something called the Joule-Thomson effect that we made a vague reference to today, and then thermochemistry, the energy associated with reactions. For gas expansions, we've done a few problems already where we're calculating Q and W. As I say here, we're going to apply some of the principles that we've learned about with heat capacity and differentials to a range of different kinds of expansions, and specifically ideal gas expansions. As I say here, for real gases, you can imagine that the systems are similar, of course, but the math's going to be more involved. For example, imagine using the van der Waals equation of state instead of the ideal gas law. Suddenly you have more variables to deal with, but really the concepts are the same. So let's define our terms here. When I mention isothermal expansions, those are the first ones I mentioned in Chapter 3. When we were first discussing them, you didn't realize it, I didn't mention it at the time, that as the system's losing energy in the form of work, it gains it back by getting it from the walls of the container and picking up thermal energy. So essentially Q is equal to the negative W. So if a system is doing work on the surroundings and W is negative, then the heat input is positive. Since those balance, both delta U and delta H are both equal to 0 because you're ending up with an ideal gas with the same temperature. In an adiabatic expansion, you're using an insulated container. If you can't replace the energy that was lost from the work that was done, the temperature will drop. T's not a constant here. Now, you can do those adiabatic expansions reversibly or irreversibly. If you do it reversibly, you get a variation of Boyle's law. Now, notice it's P1 V1 raised to a gamma term equals P2 times V2 raised to a gamma term, where gamma is a ratio of the constant pressure heat capacity and the constant volume heat capacity. You shouldn't expect Boyle's law to apply because temperature is not constant, as for the reasons I expected. As might be expected, the equation for work is not going to be the same. It's not going to be minus PdV. We'll find and we'll derive for you here that it's actually the number of moles of gas times the constant volume heat capacity times the difference in temperature. Now, if you've been paying attention here, it may seem strange. Why am I using the constant volume heat capacity? Surely the volume isn't constant because I'm doing an expansion. But here we're taking kind of an advantage from the definition of a state function. You can see from the figure that you could think of it as a two-step process. You could have an isothermal expansion, then a drop in pressure that changes the temperature. You may note that less work will be done in this process eventually, and that makes sense because you're not replacing any energy into the system from the walls of the container. So you can't get sort of extra energy out because of that energy introduction. All right, so here's an in-depth view of a reversible adiabatic expansion. So this is an expansion, imagine a piston that's insulated, and we're doing infinitesimal expansion changes. So that means the first law is going to take a slightly different form where we're using little d's. So du is equal to dq plus dw. Remember that the crosshatch is just indicative that it's path dependent. Now, because this is adiabatic, we're not allowing any heat energy to go in or out, so any change in internal energy is just going to be due to the work. And we have an expression for changes in work, minus PdV, and we're going to make a substitution of the P using the ideal gas law. Okay, so this is a reversible expansion. Basically, the pressure internal and external are going to be kept very close to each other, so that substitution can be made. You could rearrange and substitute in the definition that we learned from our previous section with heat capacity for du, and we get this expression here. Okay? Now, because I have differentials on each side, I can get rid of them and turn them into absolute differences by integrating. So assuming that over the range that we're going to look at, the heat capacity, the constant volume heat capacity is independent of temperature, I get this expression. And because for ideal gases the difference of Cp and Cv are known, I could include that on the right-hand side. If I divide through by constant volume heat capacity, I end up getting these results. Now there's a new term here, this gamma, I made reference to on the previous slide. It's something called the heat capacity ratio. It's the constant pressure heat capacity over the constant volume heat capacities. So take the time to walk through this derivation and see how you get the two terms that have asterisks in them equal to each other. On the next page, you can see that I've set those equal to each other. One little note, or a couple notes here I wrote on this gamma. Note that gamma is going to be different depending on what the gas is. Like, for example, when we learn the equal partition theorem, the heat capacity at constant volume for a monatomic gas is 3/2 R, and Cp is 5/2 R. If I take the 5/2 R divided by 3/2 R, I get 5/3 or equal to 1.67. That ratio is different if I had diatomic gas because it's a ratio of 7/5. So just a little bit of an example for some real situations. Well, the two asterisk equations from the previous slide, you could get rid of the natural logs by raising each side as exponents to the e, or applying the e function to both. You can get rid of the natural logs and do some rearranging and getting this variation of Boyle's law. That's really the purpose of the work that we've done here. Now, these are very specific conditions. These conditions for an ideal gas and a reversible adiabatic change. It's not going to be Boyle's law because of the reasons we've already said. The temperature is not constant. So you're not going to get P1V1 equals P2V2. You're going to get this variation with this gamma. How much work is done? Well, we have from our definition of du this expression, and assuming a constant heat capacity that slides through the integral sign, we end up having a very simple expression here. So this is how we generated the work for a reversible adiabatic expansion. Even though the volume's not constant, Cv does end up in the equation. So I've had some problems with recording. I hope this works. This is an example from your text that compares the results of doing an adiabatic reversible expansion to an isothermal reversible expansion back in example 3.1. So for the adiabatic, we're going to take this amount of gas, the 0.850 moles, initially at 15 atmospheres and 300 K, allowed to expand until the final pressure is 1 atmosphere, adiabatic and reversibly. The first thing we need to do, so if you remember from the previous slide, we're going to use this variation on Boyle's law. We need to find out the volume of the beginning case and the end. So you plug in PV equals nRT, use the ideal gas law to get the volume of 1.40 liters. Because we're told it's a monatomic gas, the gamma term is 3/5, and we could solve for the final volume. Once we get the final volume, then I could use the ideal gas law to get the final temperature as 102 degrees. The definition of work in this case is exactly equal to delta U. It's adiabatic because Q is 0, and we have an expression from that from earlier in the chapter. I get a work done of minus 2100 joules for the adiabatic expansion. This is a lot smaller in magnitude than the isothermal, and we discussed why in class. In the isothermal expansion, you get thermal energy from the surroundings going into the system to replace the energy that's lost in the expansion. the adiabatic expansion can also be done irreversibly. It can be done all in one shot. In this case, the expression for work is expressed as using equation 319, and applying the ideal gas law, I get this this relatively long expression here. So I think we're going to use that in an example problem a little later on. I'm going to have you, carefully look at your reading. I'll do my best to give an overview and then a little bit of interpretation of the results for something called the Joule-Thomson effect. When you have an ideal gas, the internal energy does not depend on anything other than the temperature. Remember, there's no attractions or repulsions, so you only need the temperature. The equipartition theorem guides you to knowing how much energy a sample contains depending on the complexity of the system. Therefore, if a process happens with no work, like expanding against a vacuum, there's no temperature change. If you're not doing work, you're not losing energy, so the temperature is exactly the same. James Joule did an experiment in 1845 to see how real gases would behave, ones with attractive and repulsive forces. He didn't measure a temperature change, but only because his equipment wasn't sensitive enough. He essentially had a design flaw in this expression. He thought that if he opened up the stopcock and allowed the gas to flow into the vacuum, he'd be able to measure a temperature drop in the water. But water, of course, has an incredibly high heat capacity, and so the quality of his thermometer wasn't precise enough to detect the coolness that should happen. But later he developed an alternative setup that did show a temperature change. It's a thermally isolated system. So this piston is encapsulated inside, I should say, thermally insulated container. And let me try to explain. So in this rust-colored block on the left, you're essentially seeing a gas that's under high pressure. Let's say it's 10 atmospheres. And the black barrier between it and the right-hand side of the device is somewhat porous, so that under pressure, gas can go through. Now, the opposing pressure, P2, is adjusted so it's less than whatever P1 is. So you have a thermally isolated system, slowly compressing the gas that's on the left side of the barrier, and some of the gas gets through to go to a lower pressure environment on the right-hand side. In this case, he detected a temperature drop. Now, for real gases, we should be able to predict this, right? Because molecules that have some attractions to each other are going to expand go away from each other, and that's going to cost you some energy if you're attracted to another molecule. So the Joule-Thomson coefficient was expressed, which showed essentially the rate of change of the temperature. That T bar shouldn't be there. It's the change in temperature with respect to the change in pressure. So something interesting happens when you, at a particular temperature. So I don't know if you heard Dakota there. He was barking at a student walking by, embarrassing me to no end. But I mentioned that this curve has two distinct regions. So if you imagine the device on the previous slide, again, you have the high-pressure gas being going through a porous barrier to a lower pressure area. On the left part of this curve, you see the gas cool. On the right part of the curve, the gas warms. That seems strange. What's going on? Well, first of all, let's just talk about the curve itself. This is called an isenthalpic curve. I'll show you the derivation of that on the next slide. But just for now, look at the fact that this quantity called the Joule-Thomson coefficient, it's essentially the partial of temperature over the partial of pressure. So as the pressure changes, how does the temperature change? It's basically that ratio. You're going to see a cooling on the left-hand side. That's because you are taking molecules under high pressure and they're expanding into a lower pressure. They're kind of leaving each other's attractive forces. And so getting away from that's going to lose some of their kinetic energy. They're losing some kinetic energy as they break free from the other molecules. And so therefore it cools. The molecules will warm. Notice what region of the curve you're at. You're at very, very high pressure where you actually have repulsion starting to take over. So in that case, there's a lot of potential energy between molecules, and as they go to a lower pressure area, a lower pressure volume, lower pressure space, it's like they're relieved, not to personify these molecules too much, but a lot of that potential energy of repulsion is getting converted to kinetic energy. So the molecules actually warm up. What you see on the right-hand side of this curve here is they call it the locus. So it's the individual local maximum connected as a line. So everything to the left is a cooling region. Everything to the right is a warming region. This is actually related to the liquefaction of gases. So if you can imagine, how do they make liquid nitrogen? It's done by compressing the nitrogen gas so that it escapes into a lower pressure area, therefore cooling, and then being pumped back through the cycle. And so you can constantly cool to the point of condensation. I've been having a lot of trouble with this software, so hopefully this is the last time I have to record this piece. So follow with me, if you would. What I've sketched on the top of this page is what we're calling the Joule-Thomson apparatus. So initially on the left-hand side, you basically have a gas trapped in a piston. That's what these red lines are representing, that you're applying pressure to. So you're doing work on that gas. That's why the work done on the left-hand side of this apparatus is positive. The fact that I've made the yellow lines dark is to emphasize the idea that this is a insulated container. So no heat energy is going in or out. So you're doing work on the gas, but the back wall, this blue wall, is a porous barrier. So some of the molecules are going to get through, and they're going to push against the piston on the right, which has to have a lower pressure than P1. Now, what interesting comes out of this? Well, if you calculate the work done by the gas after it has gone through the barrier, that will end up having a negative value, correct? Because it's doing work on the surroundings, which in this case is P2, or it's doing work on the applied pressure. If you manipulate the equations, you could end up generating an inequality that shows that, of course, because their Q is 0, there's no exchange with the outside world. The only energy exchange going on here is in the form of work. That the enthalpy of the before and after are equal to each other. So this is called an isentropic process. I think the most interesting part, though, is my sketch of this graph here. You could find it in your book done a little more professionally. What this is showing is that the partial derivative of the temperature with respect to pressure, in other words, how the temperature changes with the change in pressure between the left and the right, can be different depending on the conditions. In some conditions, the gas is going to cool, going from left to right. In other conditions, the gas is going to warm up. I know, that seems strange. Well, the place where the gas is cooling is on the left-hand side here. So, and if you run it under different conditions, that's the left-hand side here. Basically, what you're saying is you're dropping the pressure going through the blue wall, right? If you're dropping the pressure that's moving from right to left, the temperature is edging downwards. The explanation is that the molecules had some intermolecular attractions on the left-hand side, but that after going through the porous barrier into a lower pressure area, they kind of break free from those, and therefore sort of have to sacrifice a little bit of their kinetic energy from breaking free from those attractions. So therefore the gas cools. If you started at a much higher pressure area, the gas actually ends up warming. Now notice again, this is at the high pressure area on the right-hand side. If a gas is under really high pressure, you start having a contribution from repulsions. And that's essentially a potential energy term that is lost when you go through the porous barrier to a lower pressure area. So you have repulsions, which are converted, because you can't create or destroy energy, end up being converted to kinetic energy. The molecules are going to move faster in this region of the graph, going from P1 to P2. So it's just kind of an odd phenomenon that actually ends up leading to us being able, as I said, to liquefy gases like nitrogen. So like I said, this may be not the best effort, but I'm going to be around for office hours both Wednesday and Thursday afternoon. I'd be happy to explain this a little more clearly or go over some of the homework questions if you have questions. All right, bye-bye.